I'm Mark Cavanaugh for Cavi Coaches, and today I'm going to coach you up on conducting a lab investigation with an inclined ramp and a free rolling car. Alright, so what I have here is the same thing we had in our constant velocity lab. I've got my whiteboard ramp with my same markings. I've got my free rolling car. So I have it turned upside down because I don't want it to go ahead and roll off the table. I don't need my equipment to break. So some safety things. So I'm going to go ahead and set the car down and let it roll. And you're going to go ahead and make some observations. I know you want to see it again. We'll do it again because it's fun. Alright, go ahead and pause the video and go ahead and make some observations, and I'll put some of the observations my students have made in the past on the screen. Alright, so you've made your observations. Maybe you've decided that you said the car is gray, the car has 4 wheels. Again, we want to look at variables that we can put a quantity to, that we can measure and change. So anything that we can't measure and change, we're just going to list as a fact. So maybe you said the incline of the ramp can change. And absolutely, the incline of the ramp can change. I can put different amounts of textbooks underneath here. So that's one variable that we can change. Now, you probably said the first observation, the car sped up. So what could we measure about the car as it speeds up is the question. So we can measure how far it has gone over a period of time. So those are 2 variables that we can measure. Again, we can measure displacement or change in position and time. So we have our quantifiable observations of displacement, time, and an incline of the ramp. Any other observations that you made are most likely just facts about the car. So you said the incline of the ramp. So we're going to leave the incline of the ramp the same. It's just for simplicity. We'll get to things where we change the incline of the ramp a little bit later on in the course. But for now, we're going to leave the ramp incline a control. Okay? So we're going to leave the ramp incline a control. You may have said, oh, we can measure the speed. Oh, we've got a formula that we learned. Velocity is displacement divided by time. Remember, that's average velocity. So, and again, that's a calculation. And we'll get into variables that we have to calculate a little bit later on.
We forgot to address something in lab, so we're going to address it here through the magical power of editing. We forgot to address the car being pushed. We don't want the car to be pushed. We want the car to start from rest. It's important for the car to start from rest, so we're just going to set it down and let it go. Back to lab.
Of course. So for the time being, what we're going to do is we're going to measure displacement of the car. Remember, the markings are, the colored markings are 20 centimeters apart, and the black dashed lines are 10 centimeters. So all the way up to 210 centimeters down at the end. So go ahead and take the next couple minutes in the video to collect some data, plot a graph, and we'll come back in just a moment.
So we've finished collecting our data. Now it's time to create a graph. We're going to plot a graph. As we recall, of position on the vertical axis and time on the horizontal axis. Now you may have measured in centimeters, which you plotted the graph in centimeters, and that's fine, but we want to start using the International System of Units, or Système International, SI units. Système International is French for International System of Units. So we're going to change centimeters to meters. So you just have to convert from centimeters to meters. Centi means 100, so there's 100 centimeters in a meter. So now we look at our graph, and our graph has this curve that goes along with it. And the curve represents a non-constant velocity. Because if we had a constant velocity, this would be a straight line graph, and it's not a straight line graph. So a curve represents that it is changing velocity. The velocity, the first observation we made was it was speeding up. So that means we go to our graphical method summary sheet, and we see that we match the graph up, and we can see that this shows that x squared and y are proportional. So I'm going to change y to position and x to t squared, and that should produce a straight line graph. Next, we go to the mathematical model box, and we can see that instead of our normal slope-intercept form of a line, we're going to write the form of y is equal to mx squared plus b. Now, again, this is not our final mathematical model. We have to replace each of these. So we're going to replace y with x, open a set of parentheses for our slope. Now I'm just going to make up a number for the slope, 0.35. Remember, we're in meters, so you probably have maybe 35 or some number that's bigger in centimeters, and that's fine. Now we're going to replace x squared. We can see that we graphed t squared on the horizontal axis, so we're going to replace x squared with t squared. Now, to address the vertical intercept, we place the car down at 0 and let it go from rest. So based on letting it go from 0, our starting position still is represented by the vertical intercept. So that would represent 0, so we do not have to write the vertical intercept. This mathematical model is the mathematical model that when we graph this in our calculator and we plot our points, and you can check out my video on analyzing data using the calculator. That video is available. You'll be able to see that graph fits perfectly right through your original data because its x is proportional to t squared. So x proportional to t squared is not going to yield a straight line. Now let's say I want to try to find the velocity of the car right at this green dot that I've placed. So right at that point. If I draw this line, that line represents an average velocity. So as we get the line closer and closer and smaller and smaller distance between those, you can see that the slope gets steeper and steeper. So we want a line that at one single point, a line that just touches the curve, is called a tangent line. So we're going to sketch a tangent line. That line just touches the curve. Again, it's called a tangent line. It just touches the curve. It doesn't intersect it, doesn't cross it. It just touches the outside of the curve. Now the slope of that tangent line represents the velocity right at that point, because slope on a position time graph represents the velocity. In this case, the velocity right at that point, that is called the instantaneous velocity. That's how fast it's moving at that instant in time, or that moment in time. So the instantaneous velocity is determined by the slope of a tangent line. What we are going to do now is we're going to go ahead and collect some data from our mathematical model by finding the slopes of tangent lines using our calculator. And those slopes will represent the instantaneous velocities, which we will write in this third column, so we'll have time, position, and velocity data. From that, we are going to plot other graphs that we will look at in the next video. Have a great day, and even better tomorrow. If you found this video helpful, don't forget to subscribe to my channel, Cavi Coaches, and follow me on Instagram and Twitter @CaviCoaches.